Let's get started. Welcome to TheForkJoin. I'm one of the hosts, Oliver, and I hope that our other host, Ratchet, will be joining us soon. I think we're having some technical difficulties there, but I'm happy to introduce Jenna, who will be talking about gradual verification and all sorts of other cool stuff. Jenna, do you want to introduce yourself?
Yeah, hi, I'm Jenna DiVincenzo. I just graduated in December with my PhD, officially. And I started my assistant professor position at Purdue University in January. So I've been there I did technically do research over the summer, so technically 3 semesters, 2 semesters teaching, and oh, I'm in the Department of Electrical and Computer Engineering, actually, not the department. Well, I guess it's actually, yes, it's a department in the College of Engineering at Purdue. So that's where I sit in the hierarchy. And yeah, I do research in gradual verification, which, what does that mean? So we can
Yeah,
definitely talk about that.
that's a good introductory question when we get to the research section. But first, I'd love to ask you what got you excited about PL research in the first place? And I know you told me that you have a cool story about going to Youngstown in Ohio. So yeah, I'd love to hear about that.
Yeah, so we talked about this a little bit in the pre-show, but I'll kind of like oh, here comes Richard.
Yay, Rich
Richard.
here.
Hey
Yay.
folks,
Hello.
I was having internet troubles. Sorry, are we already live?
Yes, we just started.
I think my
Okay.
camera decided to go blurry on me. Oh well. Hopefully it'll fix itself.
Yep, I was asking
Mm.
Jenna the introductory question, which is about how she got excited about PL research.
Yeah, so I talked a little bit about this in the pre-show, but I did my undergrad at Youngstown State University, and like I said, sorry, I this was
Oh
working, but
no.
okay. Yeah, sorry. I don't know why it's not fixing itself. But
Car
all right,
technology.
we'll just go with a little bit of a blurry camera until it decides to fix itself. That way we can move along. Anyway, so yeah, actually the reason why Youngstown State University is in northeastern Ohio. I grew up in the area, and so I basically went to the commuter school that I grew in the area that I grew up with because financial reasons. I had scholarships and I didn't have to pay room and board, so I fortunately came out of undergrad without any debt. And yeah, it was kind of a natural thing for a lot of us to do in who grew up in the area was to go to Youngstown State. It actually worked out really well. It is a primarily undergraduate institution. So there's no PhD students, just masters and undergrads. And it's a smaller school. So I think max about 15,000 students. It even feels kind of smaller than that when you're actually on campus. And I was very fortunate to have some amazing faculty that I overlapped with during my time there in the math department and the computer science department. So yeah, how I got into PL research was, I had an amazing faculty there, Dr. Bonita Sharif. She actually, so it was a little bit weird. It's like, it's too faceted the way that I got into PL research. So I did empirical software engineering with Bonita, doing eye tracking and studying program comprehension through eye gazes, because naturally, when you look at something, you're probably thinking about that thing. So can we study how software developers debug and think about programs through where they're looking in the code and what order they're looking in the code.
Is
So
this
that
a
was,
common technique in software engineering research where you like track what people look at and use that data?
so I think that there is, I feel like there's a lot of techniques. I think there is an emerging community, and maybe that's changed now. I haven't worked in that community of research in quite a number of years now, so I'm not really sure how it's changed. But I think at the time there's like this community. I think Bonita was really starting to like bring the eye tracking piece into software engineering, and but there was kind of another other people that were thinking about like comprehension and how do we actually evaluate comprehension, and through different kinds of sensor techniques and data. But my research was focused mostly on eye tracking, but they were looking at things like MRI and like uh, what are they? Like things that you can just like do heartbeat or like other
Oh,
sensor
cool.
things, and that was kind of cool. Um,
And you
but there's
went from
other
doing eye tracking software engineering research to hardcore verification. How did that happen?
Yes, so that's kind of the interesting story. Well, so I kind of mentioned this in the pre-show, but I also was a double major in math and computer science. And so a lot of my computer science work was empirical software engineering, and that's where I really fell in love with like, well, one, I always kind of liked software engineering in my undergrad. I did took a lot of like we had our core focus in computer science, like the really awesome stuff they had going on was mostly focused on software engineering. So I was like, oh, I love writing code. I love watching this code work, and I love learning about techniques to make your code better. And I really enjoyed like, oh, let's do research to make software developers' lives easier, my lives easier, right? So I thought that was really cool. And then I had this whole different life in the math department where I took all these pure math classes because like I didn't care for the applied math. I actually love the pure math. I love doing proofs. I love solving, like writing down theorems and proving things. And so so it was very kind of like a very distinct lives on my two double majors in undergrad. Um, so I knew going into my PhD, I really wanted to do research in software engineering, but I loved math. I love building tools and I love studying users, but I really also loved math and math theory. So I really wanted to do something that combines all three of those things. And it just so happened one of the internships I did, like the supervisor had a connection with my PhD advisor, Jonathan, and we chatted, but it's like at that time it was so unclear if he would end up being my advisor. It just so happened to be that way. But when we had a chat, he like was like, "Oh, have you heard of this thing called like programming languages and verification?" And I'm like, "No, but that sounds cool." In the context of like building something that is user focused, but also something that has a lot of interesting math going on.
And it
And so I
sounded
guess
like it
that's
was
kind of how I
exactly
was
the
drawn that
intersection, yeah, you
direction.
were looking for
Yes.
was you get to do the hardcore math, but also apply it to real world problems and engineer real systems. That's very cool.
So I think that's really what like drew me to PL and verification. And obviously it was like this like there were no professors who could teach PL at Youngstown State University. So I didn't have any background. Actually, the way because I took too many math classes, I didn't even take a compilers class in my undergrad. So I'm like stepping into I was very, very happy that Jonathan like and Josh, both of my advisors, were very well, Jonathan Hodges and Josh Sunshine, those are my advisors for anyone who wants to know in chat. Um, I was very happy they were willing to like look at all the things I could bring and take a risk on me learning PL, like walking in. And so, yes, I obviously showed that I had an ability to do those things between all the math classes that I've done well in, and also the like, I could bring the flavor of empirical software engineering, which actually Josh and Jonathan really appreciate. But like, still, it's a risk, right? I don't have any PL background. Who knows how it's going to go?
Right, that
I
was
think
really
that's
jumping in
actually
the deep end there.
yes.
Yeah.
So I forever thankful for them taking that risk on me. And then also I do think it's a testament. So like shameless plug for like the S3D department at CMU. It's very set up well so that like students can try things and still like have other advisors. Like there were other faculty there that were really interested in my empirical software engineering research. I could very well have worked with them if it didn't work out in the PL space. But yeah, fortunately it kind of did. It was challenging at first to really transition to the different kinds of math that I was doing in programming languages versus the math that I did, like I really lean towards like pure continuous math, things like real analysis, measure theory. Um, so it was really a big change, but like through the different support systems that I had from my advisors, their students, from like interesting courses I got to take in my first couple semesters, I fortunately through a lot of hard work on everyone's part, made it through that transition and well, here I am today, right?
Yeah, I guess
So,
it's if the takeaway is that like if you are thinking about switching areas, something looks exciting but you know nothing about it, a great time to go for it is when you're starting your PhD.
Right, right.
Yes.
Yeah.
It's sort of one of those points in your career where you really get a free pass to learn something new and really dive into something in a way that it's much harder to do, I think, generally, right? Like it's a general piece of advice I often give to people starting out their PhDs is like the first couple of years of your PhD is a very unique opportunity to completely do a 180 if you want on the things you've already done. And so utilizing that effectively and in a way that is fun for you is super important. But yeah, that thanks for the background, Jenna. This is super interesting. So I want to dive a bit into something you brought up a little bit already, which is verification, right? It's one of these foundational, fundamental idea that can be traced back to the birth of programming languages as its own field. So I want you to talk a little bit more about what verification is, and I think really quickly transition into this notion of gradual verification, which is something you've been studying about in your thesis and now also as a PI at Purdue.
Yeah, yeah. So, let's see. I could pull up like my slides that might make it easier for the audience to take a look at some examples while I'm talking, but I could also just talk out loud. I don't know how you guys want to do things.
Entirely up to you, but I think we like keeping the sort of intro stuff quick, and then we dive into the stuff you specifically want to talk about with your own research agenda.
Okay,
And
cool.
also,
Yeah.
go ahead.
Yeah, so the general idea of verification is you have an intended behavior of your code that you want your code soft, and this is in the context, of course, of software. Because that's really where I do my verification is all on software, which is a hard problem. So traditionally, it's like you have some software, and you have some behaviors in your head, and or maybe written down in some like informal way, maybe in a more formal way. That would be nice. That'd be ideal. But you have some like clear picture about what you want your code to be doing, and so you try to implement it. Well, you guys know that doesn't always go to plan. You introduce bugs. You like the transition from what you want your code to be doing, or even if you are able to write it down in a more formal way, or even with English, that doesn't always translate directly to what the code should be doing. And so that's like where the like verification comes in. So verification tools are there to make sure like there are a provable absence of bugs with respect to your intended specification. Your programs do are like basically when the tools reach success, which is like very hard to get them to reach success. But if they are successful in running, and well, they return satisfiable, but that's like a little bit more detail. So basically, the idea is like when the tools say your code is successfully verified, they mean that they will provably not have bugs with respect to that specification. Well, will it have bugs with respect to other things? Yeah, but not with respect to the specification that you've given to it. And it turns out proving things about programs with tooling and designing tooling to do that is hard. And that is there's like actually two there it's kind of branched into like two different areas now. So I work on the more auto active or automatic style of verification tools. There's also these other style of verification tools that I'm not as familiar with called theorem provers. And both of these types of verification tools can be used to prove that your code is doing what it's supposed to be doing.
So I'll ask
Um,
you a question that I often get for people who are new to verification, which is why is verifying stuff with these automatic tools or writing proofs that computers check harder than writing like pen and paper proofs? Surely you just write the same thing that you wrote down on pen and paper and you hand it to the computer and it says okay and you're good to go. Like why does it seem so much harder to write a formal proof on a computer than writing it on pen and paper? Do you have some intuition for that question?
um, so I think they're trying to emulate that more with theorem provers, the whole pen and paper and transition to like just being able to like whatever you're thinking on pen and paper, transition that into something that can, well, the proofs that we want to do on code, even with theorem provers that are like trying to focus more on the actual mathematical stuff, and how you would visualize it like on pen and paper, they still involve a ton of different casework. So you really don't want to have to do that by hand because, well, so the idea of the theorem provers really are to handle a lot of the cases that humans might make mistakes on because there are so many different cases and with very minute details. And some of the cases are really just like repetitive and like not many things change between them. But so it's very easy to make mistakes with how many cases there are in some of these proofs about programs. And so the theorem provers are really there to like fill in the cases that the humans don't want to, or like may make mistakes on, and really be there as like support.
Mhm.
Now I really believe so. I don't really know the historical introduction of like when Tony Hoare decided to introduce Hoare logic and for what reason. Those are the type of techniques that inspired autoactive verifiers, which are not theorem provers. So not Rock, not Lean. I'm talking about like Daphne, or if people have heard of Varus or Viper, like really like these are tools that I think, at least this sounds right to me, probably came out of the need of trying to get closer to automation, but also get closer to what software developers are writing. So we might write pen and paper proofs about our programs and be okay with that. But most software developers are not going to want to like, or even trained in the math that they need to like, how do they represent the programming language semantics or the semantics of their program in a way that they can prove things about it. Like we don't train our students to do that, and well, we
Right.
do it if we train them in programming languages, so we don't train them on that stuff in software engineering.
Like, yeah,
So,
you said several interesting things there. Like, first, the proofs are super detailed, and different cases may be kind of similar, but slightly different, and they're easy to mess up, and that makes proving things hard. But you also compared and contrasted, like, traditional, I guess, languages like Rock, where you have to write a super detailed proof by hand, with Daphne and these other tools that you focus on that try and automate more bits of the process. Is that right?
yeah, so theorem provers really are like, well, I think there is emerging work now really trying to like help you find the next tactic or help in theorem provers or help you like fill in some of the annoying cases you don't want to. But a lot of the working with theorem provers is like working with them as an aid towards writing your proofs. So I think that's why they fit really nice. And like there is this transition of trying to get mathematicians to use Lean, because those kind of tools really fit into the kind of workflow, or at least that I think that actually was the historical reason why theorem provers came to be, is because like we wanted some programmatic tool to help people do math proofs. Um, and of course, that also translates, thanks to the Curry-Howard isomorphism, that translates to proving things about programs. So that there's that like application as well. But yeah, so the autoactive ones really are more of like, to me, it seems like, okay, well, our software engineers, our programmers, they don't really, they're not trained in mathematical proofs. And also we like automation. I think that most people that do software engineering research, they like automation. Can we automate something? And so I think both of those were like the spawning point for design by contract or horologic style verifiers or autoactive verifiers, whatever you want to call them. There's so many
Right.
names. We honestly probably should come up with a very consistent naming for
Right.
those type of tools.
Right.
But and so those are very different. So they're ones where you start with code. The code exists in the wild already, or you're writing it in a language that you're familiar with. And you're writing, well, and now we give you a logic-based specification language and you specify your behavior on that as pieces of software. So like on pieces of software, you specify what it should be doing with this like logic-based specification language. So if you've ever seen something like you have a function, you write your precondition and your postcondition. These are the type of verification tools that will take your code and a pre and postcondition. And well, it'll have to be more specifications like that if you have loops, but that's
I've
that's
yeah,
where it
I've
gets
heard
into
it
gradual
explained as like
verification.
I've heard it explained as all you have to do is write some asserts. Just pick the right asserts and it'll all work. Right.
Yeah, so that's the idea. So instead of representing your code as some kind of proofs and doing interactive proofs. Like with theorem provers, you just write assertions. Like, I mean, most coders are familiar with some, like, pick your favorite language C assertions, right? So the idea is to write invariants on your code that already exists and give it to these tools, and have them prove that your code adheres to those invariants in an automatic way. Um, Unfortunately, but fortunately for me, but unfortunately for everyone that wants to use these tools, um, it they don't normally work in the way that we'd want them to. Like, you just want to be able to write just what you want to prove about like, say you have a find max function. You just want to say in your post condition, so the return value of your find max function is the maximal element of the list. Like, that's what you want to say about your code. That's what you want to prove that is true about your code and the functional behavior. You just want to specify that functionality in your post condition, and then give your function and the post condition to the tool, and it says yes or no. The problem is it will say, I don't know, too many times.
Yeah.
And that's because you're missing a lot of other specifications that the tool needs to do automated reasoning. Things like loop invariants, things like, actually, if you talk about like lists or graphs, you need things called predicates, and those predicates can't be, especially if they're recursive in general, we can't like statically unroll these predicates, just like we can't statically like evaluate loops. So you need additional specifications that the user has to provide so that these tools can reason about all paths through your program. And so this is where they start to stop scaling well and stop being able to be used by people like broadly.
And
So
this is a real
that's where my
problem
work comes in.
because data structures are very common. You like often people use trees, maps,
Yes.
sets, all sorts of things
So
to in their
imagine that
program.
we can't do this well on basic data structures.
This is a problem.
And now look at all the other code we have today. So that is really where this field is kind of stagnated, sort of. I mean, people like me, and there's a lot of other really cool work like on separation logic, or like more ownership styled logics, like permissions logics, and some cool new work on actually well, this is like a creating deductive verifiers for these kind of verifiers for probabilistic programs. So people are working on this problem, but it's really slow going. And really, the state of the art these days is like, oh, it kind of like it doesn't even really work in a user-friendly way on very simple data structures and algorithms.
Right.
Right. So bringing this back, I think you've brought a couple of points here, right? There's sort of the limitation of the tools themselves. There's a higher learning curve, and there's the fundamental challenge that most software engineers or someone who studies software engineering is not taught sort of specifically how to use these formal tools, right? Like if you had a really great software engineering class, maybe you will sort of mentally think about the constraints that you want your functions to specify, and you would embody them in the test suite. That's one way of doing testing.
Yes.
And so I'm sure you see where this is going, but I want you to connect the idea of testing to verification, and specifically how you've been thinking about bridging those two together and sort of almost using testing as the gateway towards building more formal, rigorous testing system, and how you sort of imagine these kinds of systems evolving with large scale code bases.
Yeah, I think that is a perfect segue into my research, because uh, gradual verification is actually all about mixing these static verification techniques with runtime techniques like testing. So, and in a smooth way. So, yeah, the idea is you have to write these annoying specifications. And that's hard, and it's hard to learn, and it's hard to do, and you don't get good feedback at all. Well, you do get some feedback from the verifier, but it's more of like, hey, you're missing this specification. You figure out whether that's a problem. Well, so it actually doesn't even tell you that much. It tells you, I can't prove this. Here's what I think is why. But really the why is like, oh, uh it could be you wrote a bad spec. It could be that you have bugs in your code. But it also could just be that you haven't written enough specifications for the tool to be able to figure things out. And so starting from a place where you have well, no specifications, then you've written down your pre and post conditions, like what you want that function or like other invariants. Like you can at least write down what your code should be doing. And then how do you get all the way to full static verification? And so that's like, yeah, that's very hard. And the tool will not tell you very useful information. This like traditional static verifiers will not tell you very like nice information about
And
what's going
And
on
before
during
your
that
work, it's
process.
very all or nothing, is what you're saying. Like,
Yes,
before you
that's a perfect
finish,
summary.
yeah, before you finish writing all your proofs, it's sort of useless, right? You should have just like used the original code.
Yeah.
There's no guarantees going on. It's like all this work for nothing. Which is tragic because you might just be like missing verifying one little loop at the end that like you think is trivial in your mind, but the computer disagrees. Right.
Right.
Yeah, whereas on the other side of things, so because of these tools being so heavyweight, they're not used or in practice or in education. And on the other side of things, so we fall back to these lighter weight techniques like testing. And you can do property-based testing. So you can specify your invariants and then you can generate random test cases to try to like break that invariant in your code. So, but there's ultimately, you may not generate the right test cases. So you may not get the coverage you want. You may not be able to find the bugs in your code. You If you run that execution path, and this kind of gets towards dynamic verification as well, is you can specify your properties and then you run at runtime and it turns them into runtime checks and then like so you'll be alerted to a problem in your code and you don't have, and these are very lightweight. You don't have to specify a lot of stuff because you just run the code and check it, these specifications. So, but the problem is you can only check the paths that you run. So if there are paths you don't have test coverage for, and bugs in them, you'll never know
But it is
until you
very,
run.
it's definitely a step up from doing no checks, right? Racket
Yes.
has this notion of a contract, and it's these little checks that you put, like assertions, but they're a little bit deeper. They can be attached to the data, and they like sort of follow the data around in your program and do checks whenever you deal with the data. So like these sort of runtime techniques can be super useful in practice and a lot more lightweight than like formally proving mathematically whether something's correct. And your work is about bridging these two worlds, right?
Yes, that's exactly right. And it's totally that's so true. Like there's a reason actually at CMU, we were teaching well, I can't take credit. They're teaching like C, but a baby version of C where they incorporate dynamic verification. And so they obviously have to write their own test cases or they have test cases, but they think about writing the properties down that they want to prove about their code. It's just all checked at runtime. And so the lightweightness of that, and also one benefit of checking things at runtime is you also get some really good feedback about like what's going
Yeah, you
wrong.
get a
So if you're,
particular piece of
yeah.
data that tells you how it was violated, right? You can trace back the full history of how you got there.
Yeah, and it's totally like, and a lot of the times it lines, and because it's like that's actually what the program's doing. Like the feedback you get is really in line with the semantics of the program. So like from a learning perspective, that is like ideal, like things match. And then when you go to these static tools, actually, I was watching Will Christian's work, and actually one of the papers, I'm a big fan of his, what is it, the ownership paper.
The grounded model for ownership.
Yes, big fan, because this has been so clear in my work, but also like well, when you try to bridge the gaps between static and dynamic, which I think is really what's happening as well in Rust, very much so in its type system, in the context of ownership, of course, and lifetimes. But there's this like gap between how beneficial these static tools are, but they over approximate so badly, so that their feedback is like not useful in a lot of cases, and it doesn't match with our like semantic understanding of things. Whereas like on the other flip side, these lightweight runtime tools really do match with our like the way we think about things. However, there's downsides to them. You can't run these in production, especially if performance is an issue. Um, and I mean, there's probably a limitation to some properties that you can check at runtime.
Right.
because of like how do you check some very fancy properties, high order stuff, and how do you do that efficiently? I mean, it's part of the challenges that I have to deal with in my work because we're trying to check some of these like fancy static properties that you can specify and verify things
And
about.
it's really a
So
testament to how difficult it is to give good feedback because Rust tries very hard to give you good error messages. Like if you've seen a Rust error message, it'll be like, okay, here's what we're gonna do. You borrowed this thing. It was already borrowed over here. Actually, it'll say in the previous iteration of the loop here, and it'll like point you to all these places. And it's really an amazing error message. But still, like it's not understandable because of that over approximation. It's very hard to understand why the Rust compiler didn't like what you did. Because
yes,
this is sort of something
and
Will was
it's
saying and teeing you up for this whole thing. Like
I know
there are
I
safe
honestly should
cases,
have a
yeah.
conversation with Will.
Yeah, for sure.
Because it literally what is happening in the rest type system is very similar. And actually, I work with verification logics that are based in permissions and ownership. So like I actually think that there's very like strong overlap in what's happening. But like with the static verification tools, they very much over approximate just as much as like any other static type system type tool would be doing. And you like it does not align. And also there's like incompleteness. I really like the way he distilled it into incompleteness from the tool and then also like a mismatch of like what you expect the like semantics of the thing to be doing.
Yeah, if
So
Daphne,
there's
for example, could tell us which category our problem fell into, which is a very hard problem, that would give a lot more information to the user. But also, like, the Rust type system is much simpler than the properties you may be trying to prove in Daphne, so it
yes.
gets even harder. Yeah,
Yes, the problem gets harder because the properties are harder,
right.
and they're harder to think about and they're harder to learn about. And so, really, my work is trying to combine feedback on both sides. Well, not just feedback on both sides, but also like smoothly combine the techniques so that you can get feedback all along the way of the verification process, but also you can switch between do I want to get some static feedback on this tool or do I want to or on my code related to verifying my properties or do I want to get some dynamic feedback? And actually my case study at the end of my dissertation really kind of illuminated that you want both. In and what I kind of found when I was using the tool on like to verify a C parser was like you really want that the gradual verifier we build. It's like a baby gradual verifier, but it works on a like toy C parser, so that's kind of cool. Um, anyway, so like what I was finding is if you don't have a good like coverage of test cases, you won't be able to find that there's issues. So, but like it, and it's hard to write test cases for very complicated program execution paths in your code. So if you can get good feedback on the dynamic side when it's hot like it on in most cases that you can cover that's good for you and then you can apply in an incremental way static verification in the harder cases in a way to get some feedback when you wouldn't otherwise have any or you can try to incrementally through gradual verification get to the full static verification in those cases and then you know those paths in the program are covered from static verification. And then the ones that are hard for static verification, you can cover the test cases instead. So
Oh,
I
you're
really think
saying that
the
sometimes, like,
marriage,
yeah, the program paths sometimes they're easier dynamic, sometimes you may be able to
yes,
cover them statically, and then with those two techniques, you might be able to cover your whole program, and that's the best case scenario, right?
yes.
I see.
I think really actually though this was kind of like the biggest motivation when Jonathan introduced to me to the idea of gradual verification originally was there are some parts of your code that you're willing to put the effort into statically verifying and you want them to be fully statically verified because you get so strong guarantees from those tools. But there are places in your code where you just can't like well you either don't want to like or can't statically
Right,
verify them. And so let's do something more than nothing.
right.
And so let's do dynamic verification.
So, okay, this is sort of the interesting bit, right? Like, could you help us envision what like in sort of its most successful version, this kind of work could allow model languages to do, right? Like, I think an obvious place to think about something like this is things like unsafe and Rust, but very broadly, there's lots of interactions that happen within various subparts of a language. Within Rust, you have the safe and the unsafe dialect, but also Rust is interfacing with some C code. And so when you think about the static portions and the dynamic portions, which part seems sort of the most amenable? And have you sort of learned about some surprising places where dynamic verification is actually the right choice to do, and you should probably just avoid doing the static stuff because the marginal cost and benefit that you get from doing it is not really useful?
Yeah, those are some great questions. So I have some speculative answers,
Yes.
but like
Fascinating.
in reality, we're still really building the gradual verification technology, so we haven't used it on like really large multi-module pieces of software.
Mhm.
Verification is hard. Building
Mhm.
verification tools is hard. So hope like I mean that's my career. Hopefully we'll get there. But from what I've seen, it definitely feels like, well, one, if there's a place in your code that you really want very strong guarantees, this could be a very important module in your code, I guess, like some kernel of your code that like is used everywhere. You may want to go through the process of fully static verifying it. And the good thing is gradual verification can like incrementally give you feedback as you do that and help you get there more efficiently. To that full static verification. Because one of the things that we have seen that's really nice is the dynamic feedback really aligns with how people think about the semantics of the code and what it should be doing. So if you can get dynamic feedback on the specifications you're writing while you're writing them, then you at least know, okay, my specification's correct based on my understanding, but maybe I need to modify it in some way for static verification to work. But at least I know that like I haven't made some mistake in writing my specification because writing specifications are hard. You can introduce bugs in them just like you can introduce bugs in code. So I think that the static part or the dynamic part is very, very useful for like getting that incremental feedback while you're doing the static verification process. So
And
that's the goal for that one module. But I think the best places to employ dynamic verification is like libraries. So at the boundaries with libraries, we don't actually have code to verify them, so we can't do static verification. Actually, that's static verifiers work under the assumption that the pre and post conditions you supply on like library methods, even in the language, like the standard library in C, for example. Um, like those functions, you have to specify pre and post conditions for static verification to work. Um, but you don't have the code for the code in the standard library, so you can't actually verify that that function is doing what you say the pre and post conditions are saying it's supposed to be doing. So you have to basically the static verifier is actually in baseline not sound if you have library functions that you are including in the verification process because you don't have the code to verify it. You have to have the code. But if you can monitor those boundaries with dynamic verification,
Mm.
then you're guaranteed that at runtime, at least what you can run, like you'll protect those boundaries from the unsoundness from the static verification tool.
Right.
we had
Could you
an
talk?
interesting question in the
And
chat.
that really plays into the safe and unsafe Rust thing too that you mentioned.
Is now a good time for chat questions? So you've
Yeah.
been talking, Jenna, about like this interplay between static and dynamic and how like dynamic checks can inform your decisions about static guarantees and the other way around. We had an awesome question from Pilet Rec on if you think it's possible to extract the static assertions necessary for some part of the code through dynamic verification. So like the feedback from dynamic informing how you write those static assertions.
Yeah, absolutely. So my work so far has mostly been focused on like how can we actually marry these two tools in a very seamless and sound way. But one of the things my work hasn't done so far is like how do you actually produce or help people produce those specifications beyond just saying the ones you have written are good or not and giving them better feedback from the dynamic side and the static side. So that's actually kind of leading into some of my newer work as well. So there is absolutely work out there. I think Daikon is the traditional tool for taking runtime like information and trying to generate assertions, static assertions for them. So one of the things I'm really interested in is like how can we marry the idea, like the foundational work that I've done in gradual verification with also these works out there that are starting to infer specifications. Because like one of the hard parts is writing them. So like, well, let's give them more help other than, so my work so far has been giving them help on the like feedback side. Um, and letting them do things incrementally in a sound way. But we also need to solve the problem is like, how do you get them to write? So I think they're not only can the dynamic feedback kind of play a part in like the humans can infer information from the dynamic feedback. But we can also try to incorporate tools like DICON, like likely invariance, and try to so one of the things that's nice when you pair DICONs, likely invariance on the runtime side, is you want to pair it with a static verifier to ensure those likely invariants are actually things that should be that are good to verify or can be verified about the code. And so I think that I haven't really thought much beyond this question, but I think that there is some nice like that's already pairing a dynamic tool with a static tool. And I think that if you think of it more smoothly in the context of graduate verification, we could create a much more powerful tool from that.
Sounds like there's a
It's
good
part of like
project here. Yeah.
yeah,
And you're looking for
well,
students,
part of
right,
my
Jenna?
project, yes.
Yeah, so that
I
sounds
am looking
interesting
for
to you.
students.
Yeah. That sounds interesting to
Um,
you. You should apply.
yes.
Yeah.
Also, on the other side of things, we're actually, and this I'm kind of been, and I want to plug some other papers that I've been really inspired by because when you're a faculty or like when you're thinking of research ideas, it usually comes from inspiration from other places. And so Will Critchen's work is something I think I've been really interested now that we have a graduate verification tool of like, how do you teach people verification with this? And I think Will Critchen's like grounded conceptual model paper. So go to the other podcasts if you want to hear more about that. Like I think that was like 2 weeks ago.
Mhm.
Yeah, so go watch that. But his work I think really sets a good foundation for the kind of exploration I want to do for teaching people verification techniques with gradual verification. And then there's been this recent paper from Krista. I want to get the names right because I think it's important that you guys check those papers out too. It's called Towards AI-Assisted Synthesis of Verified Daphne Methods by like Christina Lopez's group at UC Irvine. So they are exploring how you can generate specifications and verified code in Daphne with large language models. And I think that is very cool. And so one of my spawned projects is how do we generate like specifications for verification using large language models in the context of gradual verification. Because it's really an incremental process for humans. So it's probably going to be an incremental process for large language models. And can the feedback mechanisms of gradual verification improve the learning of large language models to propose better specifications to users?
Yeah, humans aren't the only ones that benefit from making a problem incremental. If you can
Yes.
break things into smaller steps, for example, I've heard that the new GPT models are trained to like sort of talk to themselves for long periods of time, like minutes
Oh,
at a
that's
time,
cool.
giant conversations with themselves, and then they sort of don't show that, and then
That's
that you get your answer. Yeah.
sort of a standard idea in the LLM literature called chain of thought.
Chain of
So instead
thought.
of trying
Yep.
to answer a query directly, you basically have a conversation with yourself where yourself is the LLM, and you try to generate sort of steps that you would use to try to answer the question. And there's lots of like even cool theoretical papers that I was discussing with a couple of friends that show that in sort of a very rigorous complexity sense, having chain of thought enables you to have more computational capabilities in an LLM as opposed to not having that. It's like sort of fundamentally more expressive to be able to talk to yourself. And so one of the sort of related ideas I was pondering when you were describing sort of icon and how it works, Jenna, is this notion of like investigating program traces to extract assertions, right? And then feeding that into a static verifier, generating errors or sort of failed verification conditions from it, and then using that to synthesize new inputs that the dynamic tool can then look at. And so you could have this like very interesting interplay between a dynamic tool, a static tool, and an LLM that can sort of generate new
Yes.
input. That would be very interesting. Is that sort of like along the lines of what you're thinking about, or?
So yeah, actually that is you just described my career proposal.
I see.
Nice.
Yeah, so DARPA and both the career grant proposals, they want something like large and like long-term viewpoints and tooling. And so I want, like, my main goal of the research that I do is I really want everyone to be able to, as they're developing their software, be able to verify it in some way, hopefully in a very strong way. And how can we train people to do that, and how can we build tools that fit into their workflow? And I think that there is this combination of techniques now, both from the dynamic and static side and large language models, that can come together with the foundations of gradual verification, to make this technology that actually works in the workflows of software developers today.
As a
Um,
reference point,
and
I was at Amazon this summer,
yeah.
and we have full-time employees that are spending all their time writing lean, trying to verify bits of this library we have. And it just takes so much effort to verify really simple things about like lists and data structures and all that. And like when you refactor it, all the proofs break. So this is a giant problem and actually relevant in industry. That's just my one data point from my experience this summer. What Jenna is doing like could have a big impact in this area. Yeah.
Yeah, that's definitely the goal. And one of the things that I think is maybe unique about my research group, but not necessarily unique like broadly. I think there's a lot of people kind of doing this too, is I like to build these tools from with an eye for theory, engineering, and user studies. I think you can't get to that long-term vision of a tool, a verification tool that works in the workflow of a software developer without having building tools from all, like, by looking at them from all these different angles.
Oh, the dream tool that integrates nicely that the average person can use and start proving stuff with. That's what you want.
Yes, and I think you get there by taking a look at like theoretical foundations, and also taking a look at how can you build like more optimal, like optimized tooling, and then also like how do you build tools that people can use. And I think that actually my dissertation kind of illuminated this problem, even in graduate verification, that you kind of need this. Is we have this formal property called the gradual guarantee, and that basically just says that you have like as much granularity of imprecision in your specs as you want, and we won't break. So we basically won't be
Interesting.
incomplete. We won't be incomplete if you're missing specifications. We'll be incomplete if you write specifications that the SMT solver can't deal with, right? But in the context of like, because you're missing specs, we won't fail. And that's this formal, like our formal foundations is built on sound, like our theory paper's soundness and this gradual guarantee. Because we think that's going to be a property people want, right? That sounds reasonable. Well, the way that it's formulated in today is that it's actually too strong to do some optimizations that we're finding out in some of my engineering papers
Oh,
and trying
really?
to like actually optimize runtime text. Too strong because it was nice to write it that way. In terms of
Could you
what
give
people
an
would want,
example?
it's too.
That's sort of interesting.
Yeah, no, it's actually super interesting. And then just to kind of like, also we realized in my case study in my dissertation that following too strictly into the gradual guarantee also leads to places where humans aren't getting feedback they actually want from the static verifier.
Oh, wow.
Because we're suppressing those,
But
right?
the
So
gradual guarantee sounds like a good thing. How could it be
right.
problematic? We have 10
So
minutes
I think
left in the
this is,
stream. So do you think maybe this will be our last like big question is why is your gradual guarantee a problem?
Sure.
yes, I think
Okay,
that's a great question. And I
great.
wanted to bring it up because I think this is, I don't know, this is like my philosophy. I think you need to, when we build languages, for all the verification and PL people out there, or people building tools that people use for programming language things, I think you need to take a look at it both from an engineering theory and a user study perspective or user perspective, because you learn things about like what your assumptions are by checking out these other things. So our assumption was this gradual guarantee. We want to be as expressive. Well, we want you to have the like as much granularity in terms of missing specification as you want, because like in theory that's great, and then also because we need to prove properties nicely. Let's write this guarantee in a way that's also easy to prove. And we kind of kept that into, oh, actually, remind me, Richard, what your original question, because I think we're kind of back on that same track, so I could answer that. I kind of forgot what your question was
Oh,
originally.
we were just trying to get an example of this, like cases where the gradual guarantee is too strong to allow
Yeah.
for certain optimizations. Yeah.
Yeah, so let's see if I can remember the one from yes. So we actually, well, so there's two reasons why so in the original theory paper that we had, we used the weakest preconditions calculus. So for those listening that don't know what that is, go look it up. And then we switched to symbolic execution like calculus going into the actual tool itself. And that is for two reasons. The first reason is all of the tools that do separation logic or like permissions logic based autoactive verification, they are implemented with symbolic execution pretty much. So it was nice to make that switch and make that contribution to do like how do you do gradual verification with symbolic execution. But also, if you want to do very easy optimizations, basically, so the idea of optimizations and gradual verification that we've been focusing heavily on is you have all the static information, you should not have runtime checks for static information that you know. So basically, you want to reduce the amount of runtime checks you're doing based on all the static information you have given. So given the program, you get static information, and given whatever specs people write, you get static information. So along this path from no static specs to full static specs, you have you get more and more static information that you can leverage to then reduce runtime checks. So you shouldn't be checking something at runtime that you already know is true at static time is basically the idea.
Right.
So to optimize in a way that you would want to do in the context of recursive predicates and weakest preconditions, you can't do it or you break the gradual guarantee.
Because you're dropping some things and that's bad for the gradual guarantee or something like that?
So what happens is you can come up with very, very complicated algorithms to maybe come up with an optimization that adheres to the gradual guarantee. That's definitely possible. But like the very easy optimizations that you would want to like implement. So something that's not super complicated, that's kind of easy to follow and understand. The like straightforward way to optimize these ends up it's basically I won't get too much into details because I think it'll take too long and it'll be kind of hard. But the gist of it is if you want to optimize these checks in the way you would want to with weakest preconditions and folds and unfolds with predicates, then what happens is it's actually, and I guess this is worth saying, the checks don't really line up in the right place in the program. So weakest preconditions is a backwards approach. So a lot of the checks end up like not where the stuff is that you're checking is produced like from the program statements where that thing that you're checking originates from. They're much farther away from where you're actually doing the checking because you're going backwards, basically from the bottom of the function all the way back to the top and then doing checking. So a lot of the runtime checks end up like the things that you're checking ultimately, those verification conditions are much farther away from where that
Right, the
program
thing that
statement
generated the condition is down here, but the check is way at the beginning
Yes.
of the program. That's what you're saying.
Yes.
Right.
Yes. And the way we formulated the gradual guarantee is that you have to kind of do a stepwise, like things have to, you can't fail a check early. You have to basically fail it at the place that it should fail. So when something is correctly verified without imprecision, like if you add imprecision, the idea is if you add in imprecision, it shouldn't fail. So really the mismatch here is we're checking things not where they should be checked. And so what happens is we are failing much earlier than the less precise program, and that's a violation of the gradual guarantee as it's formulated now. So that's actually, but when you think about that, that's actually not that big of a problem because you're still failing in the like more precise program, your correct
Mm.
program, the fully verified program. You're still failing. You're just failing later.
Ah, I see.
And in the less precise one, you're still failing. You're failing earlier, and it's more of a problem if the more precise one is failing later because you've stepped in the states that are invalid. But if
Mm.
you're failing earlier than the more precise program, is that really a problem?
So did you find a way to relax this guarantee to handle this sort of failure at the wrong time scenario?
Not yet.
Not yet. So this is an
Not
interesting
yet.
ongoing piece of research where like
Yes.
some guarantee you thought was really useful in another context turns out to be a problem when you're doing these optimizations, right?
Well, actually, so that was solved with strongest post conditions because strongest post conditions goes forward. And so the checks end up being right where they should be.
Oh, I see.
So the strongest post conditions can be optimized in a way that adheres to the strong version of the gradual guarantee.
Oh, I see.
Weakest preconditions can get there, but it's a lot more annoying to get it there. So that was a nice benefit of strongest post conditions, and aka symbolic execution. But one of the other issues that we came across in my new work that we're working on is so we're extending gradual verification to fractional permissions. So we can now
Whoa.
specify things like read and write, and hopefully eventually concurrency, but that's a harder problem. And we're actually finding that there's a same issue with symbolic execution within this gradual guarantee because with fractional permissions, it's really hard to explain without an example, so I won't
Yeah.
go too much. I'll try to give you the overview. Basically, there's a scenario where you have fractional permissions that you kind of have if you assume something optimistically with is a read, you actually don't know how much permission, like earlier in the program, if you have a read, you don't know how much permission to assume, so you can only assume you just have non-zero permission. And so later down in the program, if you need additional permission, you have to do this check again. Because all you know is you just have non-zero permission. You don't know if you have 1/2 permission or full permission. All we know that we've done a check for so far is non-zero permission.
And this is a
So we
problem
have a
for
read.
gradual verification because you don't know what to check? Is that what you're saying?
So basically, you know what to check. We just check too many
You
things.
check too many
So if
things. Oh,
yes, so if we had a read and it was really supposed to be for like originally the program, maybe the precondition is that you're supposed to have write permissions for this whole function, but you didn't write that specification that you had write permissions. You said question mark,
right.
which is like the hallmark of gradual verification. And so when we get to a first occurrence of a read, all we can assume and do a check for is that read. And then if you actually do a write later, we have to go ahead again and actually do that write check because all we've checked is read so far.
I see.
But if we were to somehow be able to analyze the program and know that you needed a whole write permission, then we could reduce the amount of runtime checks you
I
need.
see. And reducing the amount of
But
runtime checks is good because they're very slow, right?
yes.
Okay.
And ideally in performance, like you don't want any runtime checks if
Right.
you could get
Right.
none, right?
So we have
So
a minute left. I think that was a super interesting conversation
yes.
about like the deep technical bits of gradual verification. You told us that the question mark thing is really important and that, you know, these guarantees get in the way of trying to reduce the number of runtime checks. Do you have anything else you want to say before we sign off? Recruiting students, pitch your lab at Purdue, that sort of thing?
Yeah, just one quick thing about the same topic is yeah, so in that context, also if you tried to optimize, it would break that gradual guarantee again. So we really what we want to do is relax it. And then there was other examples that we saw on the case study side where like you weren't getting because we tried to be very strong about the gradual guarantee when we built our tool. There was feedback we weren't getting that the user may want that would violate the
Oh,
gradual
I see.
guarantee. So very interesting stuff going there. In terms of my lab, I am hiring students, probably one student this year. this cycle. So I'm always looking for students that are interested. If anything here sounds interesting to you, feel free to apply. Oh, if you're going to apply, I am in the electrical and computer engineering department. You will have to apply to ECE. I can't main advise, I can co-advise students in computer science at Purdue, but I cannot main advise them. So if you apply only to computer science, you will have to find a main advisor in computer science, and it wouldn't be me. So make sure to apply to both computer science and ECE. The deadlines are different. So ECE is earlier. Usually last year it was December 1st. I think that will probably remain. Computer science is usually aware of, and the application is nice. You can very easily submit one application for both places. So just make sure to check the box for EC as well.
That's right. One last parting question for you, Jenna. What are three papers that you would recommend people read? And they can be within your field of study, they can be in anything that has caught your attention recently, or something that feels really foundational and important related to what you care about, or just you find interesting.
Yeah, that's a great question. I mean, I think I plugged a couple of them. I think the AI for Daphne paper from like Christina Lopez
Yeah, I have the
Institute.
link
Sorry, I
here.
want to make okay, great. Yes. Will Crichton's paper, fantastic paper. You guys know that. And the other paper that I really caught my eye recently is called I guess I could put it in the chat myself. Or maybe I'll just say it out loud. It's well, this is more of like a theory, maybe something I'm interested in particularly. It's called compositional symbolic execution for correctness and incorrectness reasoning. So, and that's from a group from Imperial College of London. It's a really cool paper. It actually kind of creates this nice formal foundations and basically axiomatizes things that like if you were building a tool, like our gradual verification tool is built on the same foundations as all these other static verification tools called like Viper or Jillian or Verifast. So there's these very specific types of tools that do auto-active verification and separation logic. They kind of distill a formal like basically distill the formal proofs of tools of soundness for those tools into like some axioms that you have to prove about some very specific algorithms that a lot of these tools like are built on. So I thought that was so cool because I think it's gonna like lead to some really cool work in making it easier to build graduate verifiers.
Oh, cool.
But very theory paper, so and kind of
Oh,
really
love
just
that.
like me geeking out over something very close to my research.
Wow, that's
That's
awesome.
precisely the kind of paper we wanted to recommend. Yeah.
Yeah.
Well, been an awesome time chatting with you, Jenna. I hope folks
Awesome.
both listening now and later on also find it enjoyable. Once again, Jenna is at Purdue in the EC department and looking for students or a student. So if any of this excites you, please apply to her and work on making verification great and good for everyone. Right.
Right.
Awesome. Thanks for having me.
As
And thanks for
always.
listening, everyone.
Yeah. Thanks for coming on the show. It was awesome.
We'll kill the stream now.
Okay.
Over.
Bye-bye.